first, thanks to the organizers for inviting me. So everything that I'm going to talk about is joint work with Matt Holtenkamp and Chris Putera. So today I just want to talk about two categorifications of the color-Jones polynomial. So one is Kovanov's categorification of the non-reduced color-Jones polynomial from 2003, and the other one is the Cooper-Kruskal categorification. And these two categorifications are very different. They're based on different formulas for the color-Jones polynomial, and they're still not very well understood. Properties are not known, but today I don't really want to talk about properties of these theories. I just want to ask how are the two theories are related. And a very naive guess would be that they are isomorphic, but that's obviously not possible because Kovanov's theory is finite dimensional, whereas the Cooper-Kruskal theory is infinite dimensional. And now you can ask, well, does maybe the situation change if you work in a different setting? Let's say we consider a knot in a thickened analyst, and we compute the Endler versions of these theories. Could they somehow be isomorphic? And the answer is still no, because, well, the same problem. Cooper-Kruskal's theory is still infinite dimensional. But now, what we can prove is that the two theories become equivalent for the unknot when formulated in the quantum Endler setting, so when formulated in the quantum Endler-Barnatan category. And what is this quantum Endler-Barnatan category? Well, I'll define it later. So it's a deformation of the Barnatan category. It depends on the parameter Q, and this theorem holds under the assumption that Q is generic, and by generic I just mean that 1 minus Q degree is invertible for non-zero D. And so in my talk I will try to convince you that this theorem is true, and in my talk everything will be very explicit because the proof is basically based on a computation in some sense. So I have to give all the definitions, so everything will be very explicit. And so I first will say a few words about Endler-Kovanov homology, then about categorified traces, then I will briefly recall the definitions of these two models for colored not homology, for people who don't know them. And then I will say a few words about the Cooper-Kruskal projectors that already appeared this morning, and then I'll be in Paul's talk, and then I will give the proof of the main theorem. And then at the end, I want to talk about generalized projectors which categorize other idempotencies. So first, what is Endler-Kovanov homology? Well, it's some homology theory for rings in a thickened analyst. It was discovered by these people, and it contains a lot of interesting information. For example, it can detect the trivial braid. So if you have a braid and you take its closure and compute the Endler-Kovanov homology, it can tell you whether the braid was trivial. It carries an SL2 action, and it is properly functorial under smooth link cobordisms, and it also factors through Barnatan's annular version of the Kovanov bracket. So this is complex in the Barnatan category. And then it's also related to the Chen-Kovanov tangle invariant. Namely, if you have some tangle, and you compute its Chen-Kovanov complex, it's some complex of bimodules, and then if you take the term-wise zeroth Hochschild homology, then you get a complex that's isomorphic to the Endler-Kovanov complex. And it's not just isomorphic, it's naturally isomorphic in the following sense. So before I said that the Endler-Kovanov complex or Endler-Kovanov homology is functorial under link cobordisms, and it turns out that this term-wise zeroth Hochschild homology of the Chen-Kovanov complex is also functorial under link cobordisms, and the two functors are isomorphic. And then we define something that we call quantum Endler-Kovanov homology. Well, so the idea is just to replace the zeroth Hochschild homology by the zeroth quantum Hochschild homology. So we pick some tangle, so we have some annular link, we pick an entangle whose closure is the annular link, and then we compute the Chen-Kovanov complex, and we compute the term-wise zeroth quantum Hochschild homology, and that gives us a complex, and we can call the quantum Endler-Kovanov complex. And of course, quantum Hochschild homology depends on the grading, so here the grading is just the quantum grading. It of course also depends on parameter Q, and it turns out that this theory depends non-trivially on the value of Q. So the ranks of the homology groups depend non-trivially on the values of Q. This theory is still triply graded, but now it carries an action of quantum SL2 instead of SL2, and it's functorial under smooth link cobordisms up to powers of Q. And it factors through sort of a quantized version of the Endler-Kovanov bracket. So this lives in this quantum Endler-Barnatan category. So I define it later, but you can think of it, and I'll come back after that later, so you can think of it as the quantum horizontal trace of the Born-Anton bicategory. And also, so as I said, it's functorial, so and it provides non-trivial invariants for closed surfaces in a four-dimensional solid torus. And these invariants are somehow already contained in the original quantum homology, but we never really interpreted it this way, but it does. So now I want to give some of the definitions. So I want to be very explicit. I first want to start with the quantum horizontal trace. So horizontal trace already appeared yesterday and today in Paul's talk. So I will assume that we have some bicategory C, and we'll assume it's pre-graded. So there's a grading on two morphisms. Two morphism sets are graded K modules, and gradings are additive under both compositions, and then we fix some invertible element Q. And then the quantum horizontal trace is a category. It's defined as follows. So the objects are one endomorphisms, and so there are one endomorphisms in the original category, and I will use this notation bracket F to denote one endomorphism viewed as an object in this quantum horizontal trace. And then the morphisms are given by such squares, where you have a one endomorphism at the top, a one endomorphism at the bottom, and then on the side you have a one morphism, and on this side you have the same one morphism. And then there's a two morphism in the square, and this two morphism goes from this composition to this composition. And one allows linear combinations of such squares, so basically one takes the sum of two morphism sets where the sum is over all possible one morphisms from X to Y. And then one imposes this relation. So what the relation says is if you have a piece of a two morphism on one side of the square, you can move it to the other side, but you have to pay a price. The price is that you have to rescale by a power of Q that depends on the degree. So, right? Okay. And it's often useful to think of the two sides of such a square as being identified. So we can think of these morphisms in this category as being two morphisms on a cylinder. And I will also sometimes refer to this P as the seam of the morphism, because it sort of corresponds to this blue line where the cylinder is glued together. So that's the quantum horizontal trace. And it has some nice extra structure. So if you have two one morphisms that can be composed in both possible ways, then F star G and G star F are endomorphisms, so they represent objects in the quantum horizontal trace. And it turns out that there is a preferred morphism between these two objects. This is called the cyclicity morphism. And it's given by this picture here. So you see they have one composition at the top, the other composition at the bottom, and then the seam is given by G. And what's the two morphism? Well, it's just given by identity. So you can imagine, think of this as follows. So you start with your identity morphism of F star G. You think of it as a morphism in a cylinder, and then you sort of twist the bottom half of the cylinder by 180 degrees, and then you get this picture. Now you can ask, is this morphism always invertible? And of course, to find an inverse, what you would like to do is you would like to twist the other way, or you would like to flip this picture upside down. And this works if the bicategory, so if one morphisms in your bicategory have right duals, because then the inverse is just given by this picture, where here you have the co-evaluations of the seam. And here you have some power of Q that depends on the degree of the evaluation. And so this is the quantum horizontal trace, and now I want to look at the quantum horizontal trace of the Born-Anton bicategory. So I'll leave Born-Anton bicategory already here in Paul's talk, but I quickly want to define it. So objects are non-negative integers. The one morphisms are flat, so crossingless tangles, and two morphisms are some linear combinations of dotted cobordisms, cube modulo the usual Born-Anton relations, and there's some grading on these cobordisms. So this is the quantum grading that we later use to take the quantum horizontal trace. That will implicitly assume that we allow formal grading shifts of one morphisms and also formal finite direct sums. So we look at the additive closure. And now the point is that if you take the quantum horizontal trace of this bicategory and can describe it explicitly, it now corresponds to this quantum, what we call the quantum Born-Anton category. But all the objects are just resolutions on the analysis, so closed one manifolds. And the morphisms are linear combinations of dotted cobordisms in a thickened analysis. And we want that these cobordisms intersect such a cross-sectional rectangle transversely. Then we'll call this rectangle the membrane. And then we impose the usual Barnard-Hahn relations from the last slide, but we also impose membrane relations. So these are these relations here at the bottom. So these relations tell you what happens when you push a piece of a cobordism across the membrane. So if you do that, you usually get the power of Q that's related to the degree of the piece that you push through the membrane. So this Barnard-Hahn bicategory is isomorphic on horizontal trace, just because if you have a morphism with the horizontal trace, you can think of it as a cobordism in the cube, but the sides of this cobordism don't need to be vertical. They're given by some flat tangles that correspond to the seam in the squares of the quantum horizontal trace. And then if you have such a cobordism, you can just take its annular closure, and this gives you an isomorphism with the quantum annular. And if you're interested in this category, because now if you have an annular link diagram, then you can construct the annular Barnard-Hahn quantum bracket, you can interpret the chain complex of this quantum annular. Another thing is that it's related, this category is related to the temporal leap category, so there's a functor go from the temporal leap category to the quantum annular Barnard-Hahn category, and it's just defined as follows. So if you have a flat tangle, which represents some morphism, you just take the product with a circle, then it becomes a surface in the thickened annulus, so it becomes a cobordism, and as such, it represents a morphism in the quantum annular Barnard-Hahn category. And you can ask, why is this functor compatible with this, the temporal leap relation? Well, the point is, if you cross this circle with an S1, you get such a torus. And now the relations in the quantum annular Barnard-Hahn category show that this torus evaluates to Q plus Q inverse. So the functor is well defined, but it's also there for more intrinsic reason. The point is just that the Barnard-Hahn bicategory is a categorification of the temporal leap category, so you can realize this functor as sort of a composition of functors. And then you can ask, is this functor maybe an equivalent? And the answer is it's almost an equivalent, so you have to replace the temporal leap category by the additive closure. We don't have to do that on the Barnard-Hahn category side because there I'm already allowing formal direct sums. And then you get an equivalence with this category B, B, and Q. So what is the extra B? Well, the extra B stands for Werner's relation. So this is an additional relation which says that if you have a cobordism in the thickened annulus, and if there's a dot on an essential component, then the cobordism is 0. And if Q is generic, so if 1 minus Q squared is invertible, then this relation is automatic, so that this is literally just the quantum annular Barnard-Hahn category. And then, so in other words, in this case, the Barnard-Hahn category, quantum annular Barnard-Hahn category is basically the same as the temporal leap category. And that's into the finite dimensional representation category of quantum SL2. So you can basically use these three categories almost interchangeably, at least for the things that I'm going to state in this talk, but I'm usually going to work on this side. And then another thing that I want to mention is that there's also a functor that takes you directly from here to here. And this functor is induced by taking a flat tangle. So a flat tangle is like a flat and end tangle. So this is some object in the quantum horizontal trace. And then you take its Chen-Kovanev bimodule, and you take the 0th quantum Hochschild homology. And it turns out that this induces a functor on this category, and this functor makes this diagram commute up to natural isomorphism. And I'll say a bit more about that later. But what this tells us is that we can also kind of use the quantum annular Barnard-Hahn category and the quantum annular Kovanev complex interchangeably, because the Kovanev bracket just goes in here, and then the Kovanev complex is just the corresponding complex in here. So it can kind of be used interchangeably. So I want to say a few more things about where this functor comes from. So this has to do with categorified traces. Let's try to
continue the board.
Okay, so I want to say something about shadows. So shadows are categorified trace functions. They first appeared in work, I think, of Ponto and Schulman, and later generalized them. So I'm assuming that C as before, and then we fix some category T. And again, a shadow is, you should think of it as a categorified trace function. So it's given by a collection of functors. So you have one functor on each endomorphism category of the bicategory, and they all take values in the same target category. And then if you have two one-morphisms that can be composed in both possible ways, then you can look at the object assigned to f star g and to g star f, and you want to have a distinguished isomorphism between them. So it is called also a simplicity isomorphism. And these isomorphisms have to satisfy some coherence conditions, and they also have to satisfy this naturality property. So here alpha and beta are two morphisms, and here sigma is a bifunctor which rescales two morphisms by power of q. I've written this power of q here instead of writing sigma, but I want to think of this theta as being some natural isomorphism. So this is what we call a quantum shadow. Now let me give you some examples of quantum shadows. So if you take zeroth quantum Hochschild homology, it defines a quantum shadow in the bicategory of bimodules. Then if you take, look at the functors that sends a flat tangle to the zeroth quantum Hochschild homology, if it's one of bimodule, it defines a shadow in the defines shadow in the bicategory. In general, if you have any bicategory with right rules, then there's an obvious shadow which takes values in the quantum horizontal trace. And this shadow just sends one endomorphism to the corresponding object in the quantum horizontal trace, and it sends two morphism to the square where the C is given by the identity map. And the cyclicity isomorphism is just given by the cyclicity isomorphism in the quantum horizontal trace that I showed you before. And this shadow is universal in the sense that if C has both left and right rules, so every one morphism has a left and right rule, then every quantum shadow on C factors through the universal shadow. So quantum shadows on C just corresponds to functors on the quantum horizontal trace. So in particular, this means that, for example, this quantum shadow just induces a functor in the quantum horizontal trace. So quantum Labornaton category, and that's the functor that I showed you 2 slides earlier. So that's where the functor comes from. And then I want to say one more thing about left shadow, because we often work with chain complexes. So suppose now that we have an additive bicategory, and then we can form the bicategory of bounded complexes in C. So by this, I essentially just mean you replace each morphism category by the corresponding category of bounded complexes. And then this shadow, so suppose we have some shadow on C, then it extends to this category, this bicategory on an obvious way. Namely, you can just define the extended shadow term-wise. So if you have a complex, you just apply the original shadow to each term in the complex. And we call such an extended shadow. So for example, just an example, so if this were zeroth quantum Hochschild homology, the extended shadow would be the term-wise zeroth quantum Hochschild homology. And so we call such an extended shadow a left shadow, and the cyclicity isomorphism is just given by the cyclicity isomorphisms in C, and there's some sign. This sign is needed to ensure that this is a chain map. So why do we call this a left shadow? Well, suppose now that C has left and right duals, then there is this universal shadow that is valued in the quantum horizontal trace, and then we can extend it to such a shadow that goes from that takes values in the category of bounded complexes in the quantum horizontal trace, and this is a universal left-hand shadow. But if our original bicategory has left and right duals, then this category of bounded complexes also has left and right duals. So in this case, there is also a universal shadow which takes values in this category. And because this shadow is universal, this one factors through these shadows. So this one is just a composition of this shadow with a functor. Because this one is the universal shadow, and this is the universal left-hand shadow. And now you can ask, what is this functor? So we have a functor from here to here. What is this functor? And it's maybe not so, I mean, the theorem says that it exists, and it actually gives an explicit formula, but I mean, what does it actually do? Suppose you have a morphism in here, so you have a complex here, you have a complex here, then you have a chain maps and complex here. And what you see is that here, the seam in the square is itself a chain complex. And over here, you also have squares that represent morphisms in this quantum horizontal trace, but here the seams can't be chain complexes because you're just in the category C itself. So what happens with this picture? Well, it turns out that under some assumptions that are just necessary to state more easily, so under some assumptions, this thing goes to an alternated sum of squares, where in each square, in each term, so in the jth term, the seam is just given by the jth term in the jth complex P. And that's why we call it a Lefschetz shadow, because it kind of looks like a Lefschetz number. And in some cases, this does give you a graded Lefschetz number. Okay, so that's all that I wanted to say about categorified trace form.
So is that a functor? Are you building a functor?
So this here is a functor, and I'm just saying so an object. So the objects here are just chain complexes of one endomorphisms. So here, if an object is just given by taking the termwise. It's basically a given by applying the universal shadow chain complex. But this is what it does on morphisms of the quantum horizontal trace. So the morphism here is represented by such a square, and it turns out that if you just do the computation, so this morphism gets sent to this alternating sum. So it's not the definition. So the definition of this functor follows from the theorem, which says that every shadow corresponds to a functor. But if you just do the computation, you see that this functor sends such a square to such an alternating sum. I'm not giving the proof or anything. I just want to say why we call this Lefschetz shadows. So the functor, that's lambda, comes from this general theorem. And then you can just compute what it does with such a square. You see that you get such an alternating sum. So now I want to say something about colored homology. So first discuss Michael's model. So this one is based on a formula that expresses the colored Jones polynomial in terms of the Jones polynomials of cables. So this follows immediately from a formula in the quantity group of the finite dimensional representation category. So the way this gets categorified is, so Kovanov replaces each Jones polynomial by the corresponding Kovanov homology group, and to this end, so he interprets this binomial coefficient as the number of ways of selecting k disjoint pairs of neighbored dots among n dots placed on a line. So such a selection is called a k-pairing of n dots. So for example, here we have a 2 pairing of 7 dots, because we have 2 disjoint pairs chosen from 7 dots placed on the line. And now if we fix n, then we can arrange all of the pairings in a graph. So here I'm showing n equals 4 case. So there's a unique 0 pairing, or 0 pair means a slow pair. Then we have 3 1 pairings, and then we have a unique 2 pairing. And so now we connect to such, one connects to such pairings by an edge if one pairing came from one pairing 2 dots. So there's an edge going from here to here, because if you go from here to here, these 2 dots will come. And the next thing you can do is you can interpret this picture as a chain complex in the temporal lead category. The way you do that is as follows. So if you see 4 dots, you regard it as the object 4. If you see 2 unpaired dots, it will give you a copy of the object 2. And if there's 0 unpaired dots, it will be the object 0. And then you can assign an elementary tangle to each edge. So you get some unit diagram in the temporal lead category. You can maybe anti-commute by adding some signs. And then you can flatten the picture to a chain complex by taking formal direct sums of terms that are vertically above each other. So we get chain complex in the temporal leap category, and now how do we define the colored Kovanov complex? Well, suppose we have some framed knot in R3, then we can define a functor in the temporal leap category, and this functor just sends the object n to the Kovanov homology of the n cable. And if you have a flat tangle, you can move it around the knot. This gives you some link cobordism, and this link cobordism induces a map of Kovanov homology. So you can send the tangle to this map, so this gives you a functor. Now you just apply this functor to this complex, and then the resulting complex is Kovanov's colored Kovanov complex. So that's the definition. If you do that for the end or unknot, you basically just get this complex crossed with a circle, And I want to think of this as basically this complex, but viewed as a complex in the quantum Endler-Bernoulli category. So this is Kovanov's model. And then there is Cooper-Kruskal model. So they introduced these categorified projectors that Paul already mentioned. So, and then if they have a knot K, they take the N cable, they consider the formal Kovanov bracket, and then they plug in a copy of this categorified projector, and this gives the categorification of the colored Jones polynomial. And for the unknot, this means that you just take the Endler closure of the projector. So I use this notation for this because it's kind of the class of Pn in the trace. So it's, and we want to interpret this as a complex in the quantum Endler-Bernoulli category. So now the goal is to show that basically the two constructions are equivalent in the quantum Endler setting for the But again, everything in my talk is explicit, so I have to first say more about these Cooper-Kruskal projectors. So these are just complexes in the Bernoulli category, and in the version that I would consider they are bounded above. And they're infinite complexes, and they're characterized by these two properties. So I represent them by such pictures. And so if the first property is if you attach a turn back at the top or the bottom, you get a contractible complex. And the second property is that there's a chain map from the identity tangle to the projector whose cone is homotopy equivalent to a complex whose terms are built from tangles with turnbacks. So of course here I think of the identity tangle as a chain complex supported in homological degree 0. And it's very easy to see that this is a categorical idempotent, in fact a unital categorical idempotent, so it behaves kind of like a monoidal unit. It's a monoidal unit in some suitable subcategory of the homotopy category. And so here's an example. So the projector P2 can be written down very explicitly. So it's literally the complex that you can see here. There are no higher differentials or anything. So in degree 0, you have an identity tangle. Then in each negative degree, you have a cup tangle. And then this map is just a sound. This F is given by a difference of a dot here and a dot here. And the G is given by a sum of two dots. So the whole thing just repeats itself, and then there are some grading shifts, which I didn't write. So that's the projector P2. What you see is the sort of the tail of this projector is periodic. It has this two periodicity. And now we can ask for general N, does Pn also have such a periodic model? Because the original model of Cooper-Kruskal didn't have this two periodicity. So does it also have a periodic model? And the answer is yes. So for general N, we can give such a model for the projector. So the projector is unique up to homotopy equivalence. So this will be homotopy equivalent to Cooper-Kruskal's projector. And here each box is a copy of the projector Pn-1. This map here is given by a saddle at this point, followed by homotopy equivalence. And then this map is again a sum of two dots. You could imagine that this map is a difference of two dots, but that's not the case. This map is given by a difference of an endomorphism acting on this projector minus the same endomorphism acting on this projector. And then there are some grading shifts, and there are some longer arrows, which I didn't show, but the longer arrows are just, well, they appear when you construct the complex, but they're just needed to ensure that the whole thing is a chain complex. For most computations, you can wear them. And then I want to quickly tell you how we get this model, and I want to first describe a few basic, introduce some terminology that I'll just use. So if you have some chain complex X, then so it has some given differential delta, and by a twist of that complex, I just mean any complex that you can get by adding an extra term alpha to the differential. So this alpha is kind of a perturbation. And very often we'll consider complexes. So we consider the situation where our original complex X is itself a direct sum of complexes, and where the summand are indexed by some partially ordered set I. And in this case, the twist is called one-sided if the perturbation is given by a matrix that is strictly lower triangular with respect to the partial order, so all components strictly increase the partial order. And the basic example of a one-sided twisted complex is the cone of a chain map, because it can just be viewed as a twist based on this matrix of the perturbation is strictly lower triangular. So this is an example of a twisted complex. But an important fact about twisted complex is this version of the homological perturbation lemma. So suppose now that our index set satisfies the ascending, so it's a partially ordered set, suppose it satisfies the ascending chain condition, so every ascending chain stabilizes, and suppose that for each xi we have a homotopy equivalent complex yi, then it turns out that every twisted complex based on the xi is homotopy equivalent to some twisted complex based on the yi. And here, here I say the index set satisfies the ascending chain condition. Actually, it's enough for this condition to hold in each homological degree, so the assumption is kind of too strong. So now, how can we use this to construct the two-periodic model? Well, so it goes in two steps. First, we show that there exists a chain complex of this form, with like 4 terms. So it's kind of, if you could think of it as a twisted complex built from these 2 terms. But the details are not so important. What's important is that it already kills turnbacks, so it satisfies the first axiom of a projector. But it's not a projector because it contains 2 copies of the identity tangle, one at each end, and the projector should only contain 1 copy up to homotopy. So how do we get a projector? Well, what we do is we just take infinitely many copies of this complex. So the picture continues down here. So we take all these copies, then we connect them by identity maps, and then we get some huge complex. And now this complex, there's sort of 2 partial orders that you can consider. It's the one that goes from left to right, and the one that goes from top to bottom. And this complex, so maybe I should say, so the arrows correspond to the perturbation on the one-sided twist. And this complex is one-sided with respect to both partial orders. And this partial order satisfies the ascending chain condition because the complex ends here. This one also satisfies the ascending chain condition within each homological degree because of certain grading fields. And this means, so if we now use the homological distribution lemma, it tells us that because each term kills turnbacks, the whole complex also kills turnbacks. And this is in fact a projector. It's homotopy equivalent to the Kubo-Kushka complex. But it doesn't quite look like a projector because it has lots of copies of identity tangles. Like all these terms contain identity tangles. But now we can just collapse all of these terms. And then what remains is precisely the two-periodic model. And these collapses introduce some longer arrows. So the longer arrows will not be two-periodic, but the short arrows are exactly the arrows from the theorem of the two-periodic model. And another thing that's nice about this picture is you can see that this complex is self-similar. It appears as a subcomplex itself, so there's an inclusion. And this induces an endomorphism of Pn. And if you take the cone of this endomorphism, you're just left with this piece, so you get back Qn. Okay. And now, I think, okay.
So Stefan, this is a new realization of the cross-complex projector.
We kind of, to prove that this four-term complex exists, we still need to use facts about the projector, so maybe it's not fully, the construction is not fully self-contained, but it's a new construction.
But it's a first explicit realization.
Yeah, I mean, Matt has a completely different construction, which is constructs the projector in terms of kind of a bar complex. It's completely explicit, and it's completely different. So there's other explicit stuff. Okay. But this is nice because here there are no longer, so after we collapse these identity maps, there can be longer arrows, but before these collapses, there are no longer arrows in the picture. The picture is literally just what we see. So now I think I can state the main theorem. So, and actually I have to introduce one more piece of notation. So Fn, should have defined this, Fn denotes the Chon-Swenzel idempotent. So it's an idempotent in a temporal category. And I can cross it with a circle, and then I get an idempotent in the quantum envelope of a count category. Now I can pass to the idempotent completion. In the idempotent completion, it has some image object, and I denote this by Vn because it corresponds to the representation Vn. And now our main theorem is that basically, and this actually, I didn't talk about this, but this also corresponds to a model for colored quantum which we didn't talk about. And our main theorem is now that for the Ambler unknot, all three models are equivalent in the quantum Ambler setting if Q is generic, so if 1 minus Q to the D is invertible. So in other words, if you take the annular closure of the projector, it's homotopy equivalent to the quantum annular version of Kovanev's categorification for the annular or not, and it's also homotopy equivalent to this thing. And we think of this as a chain complex supported in category 0. So this means that this projector, this is a huge infinite chain complex, but if you take its closure in the quantum annular category, it collapses completely. It collapses to something that is supported in homological degree 0. So that's the main theorem. And now how do we prove this?
So Stefan, is lowercase of n, is the projector or is verification?
This is so this is the Jones-Wenzel, but N is the Kruskal projector, and this here is your categorification in the. This here is this thing. So we're looking at the categorifications for the annular unknown. So for the unknown, Cooper-Kruskal's model is just the closure of Pn. So that's what this bracket means. This would be your model for the annular unknown, but you did the complex in the quantum. So the essential annular unknown, the unknown that goes once around the annulus. And this thing would just be this object here.
So in the top formula, you're putting the projector vertically and multiplying by S1.
Exactly.
But in the second formula, you're putting the projector horizontally on the annulus.
Exactly. So
building a complex.
I think we also called this the vertical projector model, and this would be the horizontal projector model. So, So how do we prove this? Well, I will say how we proved it in the paper. It turns, or about how we thought about it originally. Maybe some steps are after the fact, not really needed. But what we did is we introduced the notion of a Chebyshev system. It sounds complicated, but it isn't. So it's just a sequence of complexes. So each of these S's is a complex. They're all complexes in their quantum annular Natan category. We want that S0 is just the empty annular, the empty resolution viewed as a complex, and S1 is just a single circle going around the annulus placed in logical degree 0. But the important thing is that this collection should satisfy some kind of a recursion relation. And the recursion relation is that Sn should be such a cone for a specific chain map. So this chain map here is not arbitrary, but it's essentially given by some annulus in the thing. So it's given by a covariance in the typic annulus that is of the form S1 across the graph. So it's not an arbitrary chain map, but a specific chain map. So the reason why we call this a Chebyshev system is because this kind of categorifies the type 2 Chebyshev recursion, type 2 Chebyshev polynomials.
And you can define Chebyshev system in any monoidal category.
Yeah, any triangle monoidal category. So in the triangle monoidal category, this would just mean that these form an exact triangle, and then this here will be the monoidal unit, and then for this you could pick some self-dual object, and then this map will be given by the co-evaluation of the self-dual object. So yeah, you can define it in any triangle monoidal category as long as it's a self-dual object. I don't know what that value code is. But so the point is that it's very easy to see that any two Chebyshev systems are homotopy equivalent. So the terms are homotopy equivalent. But this uses, of course, that here we are not using an arbitrary chain map, but a very specific chain map. And now, the point is that Kovanev's model is a Chebyshev system by construction, because remember it was constructed from this graph with these pairings at the vertices. And there are two types of vertices, those where the last dot is unpaired and those where the last dot is paired. And those where the last dot, so if you look at the complex for n, then those where the last dot is unpaired correspond to a subcomplex that looks like this. And those for which the last dot is paired correspond to a quotient complex that looks like this. And so in Kovanev's model, this is not a homotopy equivalence, it's an isomorphism actually. So Kovanev's model is a Chebyshev system by construction. And to show that it's equivalent to Cooper-Kruskal's model, we now only need to show that Cooper-Kruskal's model is also a Chebyshev system. And what we need to show is, so if this is the annular closure of the Cooper-Kruskal projector, so we will need to show that the annular closure of Pn is given by such a cone, where An is this special chain map from a S1 cross a cup. So that's what we need to show. And for this, this is now an explicit calculation. So for this, we now use this two-periodic model. So we first want to look at, so that's what we want to show, that we have this cone formula. And of course, this only holds in the quantum annular setting. So it doesn't hold for q equals 1, for example. So it only holds in the quantum annular setting. So how do we prove this? Well, first we just use our two-periodic model. So this is just a two-periodic model. But now I'm taking the angular closure of each term. So I'm kind of looking at the universal quantum Lefschetz shadow. And what you see is that the leading term is already what we want. It's a projector with an extra strand. That's exactly what we want. Okay, so the leading term in this expansion is exactly this here. So the only thing that we need to show is that this tail agrees with the closure of Pn minus 2 and that this is the correct map. That's the only thing that we need to show. So how do we do this? Well, remember we are in the angular closure, so the top is connected to the bottom. And the first thing we do is we move the top projector with this arc around the annulus. And then we get these pictures. And these pictures, these quantities are not the same as the one up there, but they're isomorphic because we have these cyclicity isomorphisms. These are these cyclicity isomorphism from the universal Lefschetz shadow. So they're still isomorphisms. They're just chain maps from the that sort of defined by term-wise cyclicity isomorphism. So these objects are isomorphic to the top ones. And now we'd like to add differentials in the bottom row so that the vertical maps become a chain map. And of course, for this, we just have to take the top differentials and conjugate time by theta. But what does this do? Well, for example, G was given by a sum of a dot here and a dot here. And if we conjugate with theta, then so what happens is that basically the lower dot kind of stays, it gives us a dot here, but in some sense the upper dot gets moved around the annulus, and it means that it picks up a power of q squared. So we get the dot here plus q squared times the same dot. More precisely, this follows from the naturality property of the cyclicity isomorphism. So that's what we get here. So here we have 1 plus q squared times a dot, and here we get something similar. So explicitly we get these maps here. And then there are longer arrows we don't care about. And so we have these factors of 1 plus q squared and 1 minus q to the 2n minus 2. But now if q is generic, they are invertible, and then we can just drop them. And also we convert these construct projectors because they are categorical idempotents. And then we get a complex looks like this. And remember, so we still want to show that the tail of this piece is homotopic to the closure of Pn minus 2. So we have to do more computations. So what we do now is we use our two-periodic model a second time. So we use it to expand each of these smaller projections. So we express each of these pictures by such a column. And then we get the following picture. And if you look at this picture, then you see that the top right piece, which I label A, is exactly what we want. This is just a cone of a map from Pn minus 2 to Pn minus 1 with an extra strand, and you can check that this map is precisely given by the average. So this is what we want. So we have to show that the rest is just collapses. And in this picture, there are some longer arrows, which I didn't show, and we have control over some of these arrows. In particular, we can show that this piece is a one-sided complex formed from copies of these pieces B and C. You can also see directly that this piece B is contractible, and this piece C, because of these identity maps, and C should also be contractible because there are lots of identity maps. But the problem is that, so we have control over some arrows. For example, we will know that all longer arrows from this column to this column go from the top right, but we have no control over the arrows that go from here to here. And what could happen is that there are longer arrows going from here to here, and then this piece might no longer be contractible. So the question is, how do we deal with this problem? Try to compute these arrows, but they're not given very explicitly, so not so clear. So what we did is we said, well, Pn was built from copies of this four-term complex, this Qn, so we could also look at the trace of the Qn. If you do that, you get this picture. And now in the middle, you can collapse a lot of stuff, and then you get this piece and this piece. And then by induction, we know that, for example, this Pn minus 2 is homotopy equivalent to Vn minus 2. So this whole piece thing collapses to two pieces like this here. You can think of, and this is still the map that we know. And you can think of these as quantum SL2 representation, and then you see that this just collapses to a copy of Vn over here. But this map here Well, it has to be a map of representations, but it could be 0, and the problem is the same as before. There could be longer arrows, and then when we perform these collapses, it can change these arrows what to do. So we have the same problem as before. We want this map here to be 0, but non-steady 0, but it's not clear why that should be the case. So the solution that we found, maybe that's not the easiest thing, is the following. So remember that Pn has this endomorphism Un, and a very general argument shows that if you pass to the quantum horizontal trace, or this universal quantum left-hand trace, then the UN must become null homotopic if 1 minus q to the 2n is invertible. And now recall that this 4-term complex was the cone of UN, but this means that the trace the trace at Qn just becomes homotopic to a direct sum of 2 complexes, of 2 copies of Pn. And now if you go back to the previous slide, you now know that this has to be a direct sum of 2 pieces. And there are some gradient shifts, and you compare everything, and use some extra argument, and then you see that the only possibility is that Pn is indeed just Vn. And after the fact, you can see that, so this is basically shows that the Kruskal model is equivalent to the third model. After the fact, you can see that this map must have been non-zero, and you can see that this complex C must have been contractible, and then you see that this whole piece collapses, and you just get the right-hand side of the Chebyshev equation. So that completes the proof. And I should say that in a way, so this is kind of how we thought about the proof. In some sense, some of the steps are not needed. For example, to show this, we actually never used the expansion of Pn, we only used the expansion of Qn. So one could shorten the proof, and maybe there's some more intrinsic argument for why this should be true, but this is the proof. So now, in the remaining time, I want to talk about some other idempotents in the temporal limit category besides the Jones-Wenzel idempotent. So now V1 again denotes the representation, V1, the actual representation. So of course, if you have Q generic, you can look, the tensor power decomposes into isotypic components. And I denote by V and K the isotypic component of the reducible representation in K. And corresponding to this, so there's sort of the decomposition of the identity in the temporal Lieb ultra into central orthogonal idempotents. So I call them F and K. And here F and K is just a linear combination of terms that factor through Fk, the temporal Lieb category. But actually, these idempotents are completely determined by these 2 properties. And sort of the highest central idempotent is just the projector on Vn, so that's the Jones-Wenzel idempotent. So there's these central idempotents, and then there are also, so these are of course not primitive because these simples have multiplicities, but then there are also primitive orthogonal idempotents because there is a somewhat canonical, if you have V1 tensor n, there's a somewhat canonical decomposition into irreducibles. So I call them V epsilon, and here epsilon is in Zin, so these are just sequences of +1s and -1s, and then such that each prefix of the sequence has positive or non-negative sum norm. And in this decomposition, V epsilon is isomorphic to the representation in K, where K is the sum norm of epsilon. And how is this decomposition defined? Well, it's just defined recursively. Suppose we already know V epsilon, that's some irreducible representation. So if we tensor it with V1, we get 2 terms, and we just define V epsilon 1 to be the representation with the highest rate, and V epsilon -1, the one with the lower highest rate. So this is how we define this, or how we define this. And maybe one thing that you should note, so you can also think of such sequences as 2-row standard Young flows in boxes. So the first row just contains the positions of the ones. The second row corresponds to the position of the -1s, like here we have 1 at position 1, 2, and 4. So we have 1, 2, and 4, and -1 position 3 and 5. So that's why it corresponds to this diagram. And here, so what happens with this sequence, so if we add a 1, it means we add a box to the top row, and if we add a -1, we add a box to the bottom row. So I can think of this. And now, corresponding to this irreducible decomposition, there are primitive idempotents in the temporal Lieb category. And they can be defined recursively in terms of the central idempotence. Just follows from the recursive definition of the V epsilon. And if you look at the all, so So for the all one sequence, you get the transversal idempotent, and then so that the primitive ones can be defined in terms of the central ones, but the central ones can also be defined in terms of the primitive ones, because f and k, so the central idempotent is just the sum of all epsilon for which the sum norm is k. And now these things can be categorified. So when Cooper and Topobology found these chain complexes P and K, which categorify the central idempotents, and they have two properties. The first property is that you can write, so if you think of the identity tangle as a chain complex in here, supported in homological degree 0, then it's homotopy equivalent to a one-sided twisted complex built from these categorified central idempotents, and there are some longer arrows, but they all go to the right. And secondly, P and K is essentially the twisted complex formed from pieces that factor to the Kruskal complex Pk. And these two properties, there are some details, but these two properties uniquely characterize these complexes P and K. And then you can also define categorifications of the primitive idempotents, and you can just define it recursively using this formula here, using the categorified central idempotents. That's not how Cooper-Hogenkamp defined them originally. So they first constructed the primitive ones and then concluded that the categorified central idempotents also exist, but in our paper we do it the other way around. We first construct the central idempotents, and then we just use the categorified central idempotents, and we use this formula to define the categorified primitive idempotents. And now we have the following result. So if we take the closure of, I'm only formulating it for the categorified primitive idempotent. There's a similar formula for the other one. So if you take the closure of P epsilon in the quantum angular Partington category, it again collapses to Vk, where k is the sum norm of epsilon. And what's the proof? Well, so suppose by induction that we already know this result for some epsilon. And then we want to show that it's also true for P epsilon 1 and P epsilon minus 1. And for this, we use the induction and some properties to conclude that that if you take, so that you have such a mapping cone, which is homotopic to a sum of these two pieces. So this is the induction. And now, by construction, if you look at the trace of one of these P epsilon plus minus 1, it can be reduced to a twisted complex that is built from Pk plus minus 1. So this one is homotopy equivalent to a twisted complex built from Pk plus 1, and this one is homotopy equivalent to a twisted complex built from Pk minus 1. These are the two we trace. But now, by our main theorem, Pk plus 1 deformation retracts to Vk plus 1, and Pk minus 1 deformation retracts to Vk minus 1. So after applying these retractions, this complex is just built from copies of Vk plus 1, this one on copies from the Vk minus 1. And now there are no morphisms between these two pieces, so Vk plus 1 and minus 1. So after applying these homotopy equivalencies, there can't be any morphisms here. There also can't be any components in this homotopy equivalence going from here to here or from here to here. So the only possibility is that this piece is homotopic to Vk plus 1, and this piece is homotopic to Vk minus 1. That completes the proof of this generalized theorem. And maybe I want to mention an application. So for generic Q, the prior quantum Hochschild homology of Kovanov's arc ring vanishes. And the idea is that one can use the categorified central idempotents to construct a projective resolution of Hn. And then one can get the quantum Hochschild homology by just applying the termwise zeroth quantum Hochschild homology. But termwise zeroth quantum Hochschild homology is a quantum Lefschetz-Data, so it factors through this quantum angular Partington factor. In the quantum angular Partington factor, this here becomes supporting the topological degree 0 and kind of proves the result.
Questions? If you force Q to be a root immunity,
then it won't be. We don't know in general how it depends on root immunity, but the way how this
is essentially subjective.
So the way how the project started, maybe when we first defined quantum angular Kovanov homology, we didn't do many computations, but we just considered the 2n angular torus knot. And you can see that if Q is generic, it just collapses to something in degree 0. And then if Q is equal to 1, it's just the usual analytic monopomorphy. If Q is minus 1, it's the same. And then there's one more case which occurs if Q is I or negative I. So that's how the whole project started. But in general, if it's a root of unity, this theorem is certainly not true. But I think we didn't think about what happens for a general root.
If Q is a root of unity, you cannot construct all the idempotent already in the categorified case. So
that's true.
you
That's
get
so that part doesn't make sense. But you could still ask whether Kovanov and Kuper-Kruskal model is equivalent. Those are still defined, but this vertical projector model is not.
You get at the end when you cannot go forward, you get a projector on a projective non-simple module. Mm-hmm. So maybe this could be.
It's like if you crank up the order of the root of unity, you would approximate the Oshut homology of Kovanov's arc rings. So it feels a bit like in Simon's talk, where the p-canonical basis approximates the characteristic basis.
I see.
And these are important, right? The homologies of endomorphism algebras in the DG trace. And
Tasks. So there is an annular version of arc rings, right, on an annulus.
Yeah.
You also have an annular U version of arc rings, where some of the arcs go through this membrane.
Are there any other situations where it's interesting to consider these membranes? Like, if I took the APS construction, with some membranes in it.
You mean for general surfaces, or?
Yeah, I'm not really sure.
You could. We didn't really do it, but you could. I don't know.
For example, we use it in this Gilmour construction, so to relate. So basically, you see they use different filtration, and we conceptualize this, and brought the whole twisting. So it's actually just construction for a twisted quotient homology. This membrane realizes the twisting just on one side, and also the Sabas are doing twisting, so using some filtration different points. So it's so to my taste, it's less conceptual than this.
Feels like a bit like TQFT with defects.
Yeah.
Can you maybe say again, somehow, what's the role of Berner's semi-simplification? How important is that?
Again, it's automatic. So it just says if you have adopted an essential component, the component is 0. But this is automatic if 1 minus q squared is invertible, because if you slide a dot once around the annulus, if you push it through the membrane, it gets rescaled by q squared, so it's 0 anyway. But if you're at q, if you're just annular Kovanov homology, then this Bernoulli category is not equivalent to the temporal leap category, but it's equivalent to some dotted temporal leap category. So you have dot on the tangles, and then there are some. So basically, the relations are that. So of course, 2 dots. If you do Kovanov's theory, 2 dots and arc are 0, but there's one more relation, which that if I've looked like. So, yeah, one more relation. Like if I have something like this, then this plus this is the same as. So this would be the relation, and maybe this here is 0. So this would be the extra relations that you get in the dotted temporal leap category. The it's equivalent to.
More questions? Let's thank Stefan again.